This video is an application example of the energy conservation principle, mechanical energy of flowing fluid, control volume analysis, and efficiency of energy conversion. It's a very comprehensive example. It's from the 6th edition of the Tsengel and Bose textbook. A gasoline pump consumes 5.2 kilowatt of power. Gasoline flowing through the pump with its pressure increases by 5 kilopascal. Changes in gasoline velocity and elevation are negligible. Here we need to determine the maximum possible volume flow rate of gasoline. Okay, we define the pump as the system. More specifically, we define the inner volume of the pump through which the gasoline flows as the system. It's an open system, or it's a control volume. The energy in the system does not change with time if the process is a steady flow process. So we have we can use this equation. This equation, dE system over dt, should be 0 because the energy in the control volume, there's no change if it's steady state. Therefore, the rate of energy input into the control volume must be equal to the rate of energy output from the system. Now let's take a look and see what goes into the system in terms of energy transfer and what comes out of the system. We have a work input into the pump. Now a pump must be driven by something. Typically, or it could be an electrical motor, and in the gasoline pump case, it's most likely a electrical motor. That's the case in most automobiles, and also in gas stations or petrol stations. So there's work input into the pump, and mechanical energy entering mechanical energy in the entering gasoline. So the gasoline that enters the pump, there is mechanical energy in that gasoline. Energy that's coming out of the system includes mechanical energy in the exiting gasoline. So there's energy in the gasoline leaving the pump. Since this is a machine, the machine must have some sort of wasted energy. We don't know what that is. We just say there may be wasted energy. Okay, wasted energy also leaves the control volume. Now let's write the energy balance equation. We have the work into the pump. This is this term. And we have the mechanical energy in the entering gasoline. This is this term, which includes the mass flow rate of the gasoline and the mechanical energy in per unit mass of the gasoline. The mechanical energy in the gasoline leaving the pump is this term. We also have this form of energy wasted. It's also expressed as a time rate of energy transfer. So here we have one thing that we actually applied implicitly. We didn't say it, but this is actually, we applied mass conservation. We applied mass conservation principle so that we know the mass flow rate of gasoline into the pump must be equal to the mass flow rate leaving the pump. Okay, now let's go to the next slide. All right, let's further proceed from this energy balance equation. The question asks, what's the maximum flow rate of gasoline that's possible? You take a look at the equation, you see that the maximum, we don't know the mass flow rate yet, so we want to find the maximum. The maximum is only possible when this is 0. Okay, so when that's the case, we can rewrite the equation in such a format. Okay, then we can rearrange this equation because we know the pump work. Let's rearrange the equation. We get this. We can because we can neglect the changes in kinetic energy and the potential energy. as the problem statement implies, we can consider only the pressure or the mechanical energy due to the pressure change. The mechanical energy change due to the pressure change is this term. Okay, now we equate the pump work input to this expression. This expression is derived from the energy balance equation. Now we rearrange that equation, we get the maximum volumetric flow rate of gasoline, which is about 1.04 meter cubed per second.